birthday, my team members, Arana Salazar Sara Alejandro, Romano Zuna, Ditsi Yolanda, and myself, Ortega Ruiz Jose Jair, we're going to talk about the linear model of a physiological system, the renal excretion. In content, we have an introduction, a description of the system, a mathematical model, an in silico experimentation, and the biological implications. So starting out with the introduction, we know that the kidneys are the main means of waste elimination products from the metabolism that the body does no longer need. And as blood passes through the kidneys, most of the substances that the cells no longer need, like the urea or the uric acid, the ions excess, and the water that is extracted from the food must be removed as quickly as possible. The body produces it, so these doesn't accumulate in the extracellular fluid. So here we have the kidney. The blood flow enters from through the renal artery, and there it divides into the renal vein and the ureter, where the waste elimination goes through. Now, in description of the system, we know that the kidneys perform their function by first filtering a large amount of plasma through the capillaries of the glomerulus into the tubules and reabsorbing it into the blood. This reabsorption must contain the substances that the body does need, like glucose and amino acids, the correct amount of water and ions. So the tubule regulates the concentration of salt, water, and the waste products that are excreted through the urine. The filtered blood must leave the kidney through the renal vein and flows back to the heart, while the urine leaves the kidneys through the ureters until it reaches the bladder so it can be excreted. And among the dysfunctions that the kidney can present, there is the renal failure, which this occurs when the kidneys suddenly lose the capacity to filter the waste substances from the blood. One of the causes that the kidneys loses this capacity is that the urine that comes out of the drainage tubes is blocked and the waste cannot leave the body through the urine. And this causes that harmful levels of waste can accumulate and the chemical composition of the blood becomes unbalanced and it could cause the death. Okay, now presenting the model of the circuit, its elements and its representation. We have the circuit on the left side, where PA is the entrance of the artery where the blood enters the system, and it represents our main branch where the blood flow must first pass through an arterial resistance, and after that it passes through an inductor that represents the opposition of the blood of the flow change, where the flow is represented by Q1. After passing by the inductor, it occurs the glomerulus filtration, where the flow divides into two more branches that represents the vein and the ureter. The flow passed through the vein is represented by Q1 minus Q2, where it first passes through the venous resistance, and then there is the vein blood storage represented by the capacitor CV. After passing by that capacitor, the blood flow is leaded to the output of the vein, and it's redirected to the heart. And on the other branch, where the flow is Q2, and the branch is represented by the ureter, we have a ureter resistance and a ureter capacitor, where the capacitor represents the ureter waste storage. And here we have the point where the capacity of waste storage is going to be measured. In a healthy state of the physiological system, we must have an approximate range of the values of an arterial resistance of 3.24 mercury milligrams per second over millimeter. An inductor, or an opposition of the blood flow, of the change of the blood flow of 0.04 milligrams of mercury per second per square second over milliliters. The vein resistance has to be around 5.38 mercury millimeters per second over milliliters. The capacitance, or the blood storage in the vein, must be of 0.0001. The ureter resistance is about 2,812.5, and the capacitance, or the waste storage of the ureter, is about 0.00001. And in an unhealthy state of the kidney, the only elements that change are the ones in the ureter, where the resistance changes to 3,000 millimeters of mercury per second over millimeters, and the capacity, or the waste storage of the ureter, changes to 0.00015 millimeters of mercury per second no, sorry, it doesn't. Okay, so it changes to 0.00015 millimeters of mercury powered by -1 per millimeter.
We are going to talk about the mathematical model. So these are the main equations. To obtain the first equation, we analyze the first loop, and in which the input PA is equivalent to the sum of this, where RA is multiplied by Q1 and the inductor LA is multiplied by the derivative of Q1, and RB is multiplied by the difference between Q1 and Q2, and 1 between CB is multiplied by the integral of the difference of the currents. To obtain the second equation, we analyze the second loop, and this part was obtained in the same way that we did before. So this is equals to the sum of the RU multiplied by Q2 and 1 between C1 multiplied by the integral of Q2. We took the output in this point, and this is equivalent to 1 between Cu multiplied by the integral of Q2. So to obtain the integral differential equation, we solve the first loop equation to Q1 and the second loop equation for Q2, and the output remains the same. In order to obtain the transfer function, we apply the Laplace transform to the main equations, and then the second equation was solved for Q2 and then was substituted in the first equation. In this form, the input voltage is PA is with just one variable Q2, and the output PU is also in one variable Q2, and that was eliminated. And we obtain A3 equals to this, A2 equals to this, A1 to this, and A0 to all of this. And this was necessary because the equation, it was so long. So we have S in the third order. Okay, now in this part, in silico experimentation, we have here the block diagram that we use in Simulink, and the input is PI. This enters to the healthy block and the acute kidney failure. But in acute kidney failure controller, where we have the PAD, the input is a healthy one, and we have a negative feedback. So in the scenario of the healthy, inside the block, we have this structure that it is the integral differential, and these are the values. For the block diagram of the sick one, we have the same structure, and we only change the values of RU and the CU.
Hi, I'm David Arana, and I'll be starting by telling you the controller that we decided to use in our system. First of all, we based on our open loop response to determine which controller best fit our system, our closed loop system. The controller that we decided to use was a PID controller, and the values that we used for each controller were 100 for P, 4000 for I, and 0.1 for D. These values were obtained in a tool named Tuned in Simulink software. And based on these values, we obtained the next parameters I'll be telling you in table 2. You can see them. The rise time we obtained was 0.00143 seconds. The settling time was 0.00308 seconds. The peak stayed at 1 volt. This means that it didn't have an overshoot, and that's good. The closed loop stability, it was just stable, which means it's great. It was a great answer. Now I'll be telling you about our Simulink system response. First of all, the purple one is the input in our system, and the blue one is the healthy patient, which clearly has a lower amplitude than the input, and the sick patient has an even lower amplitude. Now we can see that the controller is overlooped in our healthy patient. This is a good signal because clearly our controller was a good choice, along with the values we used. Next, we have our multisim circuit. This is the circuit that we chose to obtain the answer in closed loop in our closed loop system. Now, we can see up in the left that we have our circuit for our patient, for our healthy patient. Those are the values for our healthy patient. Now, down the right, we have the same circuit of the patient, but this one's the sick one. We changed some values in these components. That's why it's the sick one, right? And in between, it's the controller. Now, the four components, elements, sorry, the four controller elements, we needed to assign some values were CR, CE, RE, and RR. Now, there are some formulas that we use to obtain these values, but we first needed to propose a value for CR, and that was 1 microfarad. And now, having the values for our PID controller and the proposed value for CR, we were able to obtain the missing elements values for CE, RE, and RR. This is our multisim system response. Now, it's clear, just as in Simulink response, that the input has a higher amplitude than the controller or the healthy one that's the green one and the blue one. Now, the healthy patient has, as I just said, a lower amplitude, and the controller is overlap the healthy one. And in our MATLAB system response, we have, just as in multisim, an input with a higher amplitude than the healthy one, and our controller overlooked in the healthy patient. Now, I'll be telling you about some pros, the advantages and disadvantages in each software. For starters, in multisim, it's a really friendly software, I would say, and it's easy to obtain an answer because without having the specific values, you only need to design the circuit you want, and you'll be having an answer. Now, the disadvantages are that you need to, there's no tool for the software to propose you the values that best fit your system. So you'll be needing to move between the values, the numbers, and this can take a while, and that's the disadvantages. It takes a while if you wanna use that software to choose the values for your system. In MATLAB, it has the advantage that, well, you have the control over all what's happening, but it's I would say that in the disadvantages, not everyone knows the coding, so it's complicated to write down the code, and there can be a lot of errors thanks to the syntaxes, so you need to know that very well. And also because we, unlike some other projects we've developed, we had to do something different, because based on our diagram in our controller, for your controller to overlap the healthy patient, you need to use the values of the sick patient in the circuit, but have as an input the healthy patient in the controller, in order for the values in the healthy patient circuit to for say fix or compensate and have the obtained answer that we want. So to realize that, it took us a while. Now, Simulink is and also, I would say, friendly software, and it's easy to use because you need to be doing diagrams. The disadvantage is that you need to know what you're doing, and so by putting some elements, you need to know which one do you need, you really need. So, and it has an advantage over Multisim and MATLAB, that it has the tune tool that it helps you to not be to not move the values for the controller by yourself, but it proposes you values that best fit your system to obtain the answer that you want. So that's a big advantage on Simulink software.
Now, on this final section of the work, we're going to talk about biological implications, where the acute kidney failure obtained answer presents a lower amplitude because of the increase of the resistance of the ureter, R, which is Ru. This implies a bigger fluid resistance because of the tubes that have been blocked, and so it's impossible to excrete the same waste substances in the urine.
The second biological implication is that the patient presents expression difficulty. The fact that the response obtained has a lower amplitude implies that the input to the ureter has a lower volume quantity of fluid filtered. As there is a smaller volume, the excretion of urine is lower, so the patient has difficulty to urinating, and all of this leads to the idea of the patient having a renal disorder like acute kidney failure.
That's that. The implementation, I'll be reading this and I'll be explaining it. I'll be explaining this later. The implementation of our PID controller made the obtained response to overlap the healthy one. This is something we've been talking along uh, the presentation. So it was clear that the use of the PID controller was the best option, because as we saw in our responses in our different softwares, the controller always overlooked the the healthy patient. So it was clear that the obtained response was the one we expected. It was there was going to there was going to there it was there wasn't going to be a better answer, and I will dare to say that there weren't going to be better values to put in our controller for the answer to overlap our healthy patient.